just tell you a story. This story is how Finastra adopted containers and Kubernetes to really drive our future strategies for enterprise security. Finastra, as you may not know, is a global financial technology provider. We're one of the world's largest financial technology providers. We have 9,000 customers in 130 countries. 48 of the world's top 50 banks use our software. We have products that range from banking cores to lending to payments and anything else that you can find in a bank. My role within Finastra is to help drive cloud strategies and build no-ops practices throughout our organization. Part of our real strategy or our real drive to adopt Kubernetes came about 2 years ago when we started a project to build an open API platform that would host APIs for the vast majority of our product lines. Kubernetes allowed us to be able to have security that was very robust, and it would allow us to have a drive that was an increased cadence out to production. Since we were already planning on using the industry standard of Kubernetes, and we partnered with Microsoft to host our IaaS workloads within Azure, we figured, let's see what Microsoft can do for us in Azure to run Kubernetes. About 2 years ago, the only way that you could run Kubernetes, or the best way to run Kubernetes in a semi-managed state in the cloud, was using Azure Container Services. Azure Container Services provided a simple but stable solution. You could do certain things through the managed objects in Azure that would allow you to scale up and down. The problem was after you started layering things like role-based access control and ingress, there wasn't much else you could do. So we quickly hit a wall, at which point we needed to start looking at what else was available. The next stage for us was moving to ACS Engine. ACS Engine is an open source project that is really the underpinnings of now AKS, but then ACS. The ACS Engine project builds ARM templates, which you then would deploy out to Azure to get a vanilla Kubernetes experience on the cloud. This was great, as it allowed us to really progress and start doing things with security, but it was also bad because it was completely unmanaged. This meant that we had increased overhead at all use cases of Kubernetes in Azure. What this meant was that when we tried simple operations that worked on ACS, like scaling up and down, we would quite regularly break our clusters. When we were starting to really figure out how difficult this meant for us to run Kubernetes in the cloud, Microsoft released general availability of AKS. For us, AKS was huge. It was a fully managed Kubernetes experience in the cloud. Because it was vanilla Kubernetes, and Microsoft was committed to patching upstream Kubernetes to bring fixes to Azure, it meant that it was full-featured. We'd be able to layer role-based access control, ingress, Calico network policies, anything else that we really needed to. And we'd be able to forge an engineering partnership with Microsoft to really drive the backlog to ensure that we'd be able to use it in production. Since we were committed to working with Microsoft and committed to working with Kubernetes, we now had our go-forward strategy for using Kubernetes in the cloud. What we needed to do then was figure out from internal standpoints what it would take to run those Kubernetes clusters, not in development, but in production. That meant reaching out to our information security departments and figuring out what their requirements in production were. After a series of meetings that were oftentimes somewhat cringeworthy, we came up with a pretty comprehensive list of what the requirements were to run Kubernetes in production, at least from the standpoint of traditional information security. The first of the three that I will go over today, information security required us to have managed patching in the cluster. Now this wasn't being done through any sort of cloud-native solution. They wanted us to actually use the existing IaaS patch processes that they had in place. These weren't cluster aware, and in fact, we couldn't even figure out a good way to schedule patches so we didn't have cluster reboots happening simultaneously, which of course caused an outage. In addition, and this is one of those cringeworthy moments, they were actually telling us that we needed to patch the containers that were running at the time. Anybody who has run containers probably knows you don't run patches on containers. Two, they wanted us to use the pre-existing hardened node and container images. These were images that would be stored in a repository managed and maintained by staff within the Information Security Department. Because we were never really able to be sure if patches had been run on a given day, or if patches were really kept up to date, because it was a manual process, this was suboptimal. We'd never know if we were actually rolling the vulnerability out to production. In addition, because it was a corporate standard image, these big images would have base software installed, like antivirus. The premise being, from the Information Security Department, you could never really be sure who was logging into a VM to do what action. On Kubernetes, when was the last time you really logged into a node? The last thing that they really wanted us to focus on was how IP traffic would be segmented. In a standard IaaS world, you have your three layers, your presentation, your data, and your service layer. Those are traditionally segmented, so that way you don't have to worry about crosstalk. In a Kubernetes cluster, you can be running all three of those layers in one cluster. So from the information security perspective, they wanted us to actually try to implement IaaS-based firewalls between services talking to each other. This wasn't really things we wanted to do. So what we came up with was a list of about 7 things that we would be able to implement that would meet those security requirements. We figured out a series of tools, the first of which, Azure DevOps, would meet the needs of CI/CD standardization and automated container hardening. The next, Aqua Security. This allowed us to build in right away that hardened container or the container vulnerability scanning. Next up, we needed layer 7 protection. We already were utilizing F5 gateways within our cloud offering, so it made sense to put one of those at the edge too. For cloud Kubernetes network segmentation, we looked at Calico, node patching on AKS managed by Microsoft. Role-based governance was all right there. And all of this really fed in to building that no-ops pipeline that we were looking for. As I mentioned, the first of these tools was Azure DevOps. Azure DevOps didn't just drive our code. Azure DevOps also drove our infrastructure deployments. We built a service catalog of ARM templates and scripting configurations that we'd be able to reuse throughout all segments of our application lifecycle. If any product throughout our company needed one of these standardized components, we would be able to go out to our service catalog, anybody on our team, and they would just reuse the existing templates and configurations, and we would have a security hardened method for deployment. In addition, because of that consistency, we were able to make sure that logging and monitoring and any audit tracing that we needed was all enabled from the get-go. All of this compounded to really accelerating our infrastructure deployments. Next up, we had to really look at how we handled the code. When handling the code, we needed to be aware of how we are building the code. Code in an instance of Kubernetes is, of course, a container. To build those containers, since we were using a standardized Java platform, we realized we could use a standardized template. Microsoft has released YAML build pipelines. Using a YAML build pipeline, we were able to create a pipeline as an artifact of code in a repository. That meant we could put an SDLC around that build pipeline and have notifications of changes, have an actual review process around our build. In addition, we could reference that as a master template that all services could use. So rather than having each individual service having its own snowflake configuration for builds, we're able to reference and reuse. Those standardized build templates would have all of our base information security hardening profiles, code quality gating, static code analysis, open source vulnerability scanning were all included out of the box as long as you reference the master template. In addition, we showed the information security team how if we pulled from master repositories, the images would have been used for the containers would actually be patched at the source. It was continual patching. Anytime we would pull something down, we'd know that we would have the latest version of those images. This also meant that once we built those containers, we could run something like Aqua against them to determine what our whole container vulnerability profile was. Each step was gated to ensure if something failed, our build process would stop and we wouldn't be able to release that code out to production. Once again, building security in from the start. The next segment that we really had to cover was how we handled network security within Azure. To drive the security layer, we couldn't have a public cluster. That's bad practice because you don't want to have people having direct access to your clusters. You don't want to have even the chance of exiting that sandbox. So what we did is we put all of our clusters internal. The worker nodes were fully internal, and we used a web application firewall to scan and proxy all of that traffic back to the clusters. After the traffic would pass the web application firewall, it would send that traffic to one of two different sides. It would either go through the API management instance, which would apply API policies, and then route traffic through a second ingress controller, or it would connect traffic to the web end that was in the web front end that was running in our Kubernetes clusters, and that would go through the first ingress controller. Having multiple ingress controllers allowed us to really segregate the traffic that was coming into the cluster and provide visibility as to what traffic is coming from where, so we could figure out better how to scale and audit what was being done in our clusters. And here's George with the demo of Ingress.
Cool. Thanks, Eric. So just for the, I think, small number of folks that did not raise your hands and are already